There is a number that every food scientist, every military logistician, every emergency management professional who has ever worked a sustained disaster response knows, and that virtually no civilian preparedness practitioner has ever been asked to genuinely reckon with in its full implications. That number is 4. 4 hours. That is the maximum time that the United States Food and Drug Administration, the United States Department of Agriculture, and every food safety authority in the developed world specifies as the safe window for perishable food to remain in the temperature danger zone between 40 degrees Fahrenheit and 140 degrees Fahrenheit before the bacterial load in that food has reached a level that creates meaningful risk of foodborne illness in a healthy adult consumer. 4 hours is the threshold below which the risk is considered manageable and above which the risk is considered unacceptable. And in a grid-down scenario, in a blackout that extends beyond the first few hours, in a collapse event that eliminates refrigeration for days or weeks rather than hours, that 4-hour threshold is crossed by virtually every perishable food item in a typical American household within the first day, producing a food safety catastrophe that unfolds in slow motion, invisibly, in refrigerators and freezers and pantries across the affected area, converting what looked like a substantial food resource into a biological hazard with the potential to incapacitate the very people who need their full physical and cognitive capacity to navigate the emergency that is simultaneously unfolding around them. The scale of this problem in a real extended blackout scenario is something that most people have never calculated, and the calculation is both straightforward and deeply sobering. The average American household contains approximately 3 to 5 days of food in various forms, distributed across a refrigerator, a freezer, and a pantry. Of this food, the proportion that is genuinely shelf-stable without refrigeration, meaning food that can be safely stored at room temperature for extended periods without meaningful degradation of safety or nutritional value, is typically a small minority of the total food inventory. The remainder, the dairy products, the fresh meats, the deli items, the cooked leftovers, the opened condiments, the fresh produce, and the significant fraction of frozen items that cannot survive extended thawing, becomes a food safety liability within hours of refrigeration loss. In a grid-down scenario that extends beyond 24 hours, a household that has not taken specific, scientifically informed actions to address this food safety transition will have lost the majority of its refrigerated and frozen food inventory to bacterial contamination, and it will have done so without any reliable sensory indication that the loss has occurred, because the bacteria responsible for the most serious foodborne illness consequences, Salmonella, Listeria, pathogenic Escherichia coli, and Clostridium perfringens, do not produce the odor, color change, or texture alteration that people rely on to identify spoiled food. The food that kills you in a grid-down scenario does not smell bad. It looks completely normal. It tastes essentially normal. And it contains a bacterial load that will produce incapacitating gastrointestinal illness in a healthy adult within 6 to 48 hours of consumption. The misunderstanding that makes this threat so lethal is the conflation of two categorically different food deterioration processes that share some surface similarities, but that operate through entirely different mechanisms, produce entirely different products, and require entirely different responses. The first process is spoilage, which is the degradation of food quality through the activity of spoilage microorganisms, primarily certain bacteria, yeasts, and molds that produce the sensory changes, the off odors, the visible mold growth, the slime, the color changes that people use to identify food they should not eat. Spoilage is primarily a quality issue rather than a safety issue, because the microorganisms responsible for spoilage are generally not pathogenic and do not produce the toxins or cause the infections that result in serious illness.
The second process is pathogenic contamination, which is the multiplication of disease-causing microorganisms in food to concentrations sufficient to cause illness upon consumption. Pathogenic bacteria are not the same organisms as spoilage bacteria. They do not generally produce the same sensory changes as spoilage bacteria, and their presence in food cannot be reliably detected through smell, appearance, or taste. This is the foundational food safety principle that the 4-hour rule is designed to address, and it is the principle that most people have never internalized, because in a normally functioning food system with continuous refrigeration, the risk of pathogenic contamination in household food is managed by the temperature control that refrigeration provides, and the sensory evaluation of food quality, while an unreliable safety indicator, is rarely catastrophically wrong, because the food safety system as a whole provides redundant protection that sensory evaluation alone does not. Remove refrigeration from this system. Extend the time horizon from hours to days, and the redundant protection disappears entirely. What remains is a household of food that looks, smells, and tastes essentially normal, and that is, in a meaningful proportion of cases, genuinely dangerous to consume. The people eating that food, under the physical and psychological stress of an ongoing emergency, with limited access to medical care, with water availability potentially also compromised, are maximally vulnerable to the consequences of foodborne illness. The dehydration that accompanies severe gastrointestinal illness, which in a well-resourced normal environment is managed with oral rehydration solutions and, in serious cases, intravenous fluids, becomes potentially life-threatening in a scenario where clean water access is limited and medical care is unavailable. The physical incapacitation that accompanies serious foodborne illness, which in normal circumstances means a few miserable days at home followed by full recovery, in a collapse scenario means days of inability to perform the physical tasks that survival requires, inability to maintain perimeter security, inability to gather resources, inability to care for dependents, and in the case of vulnerable household members, the elderly, the young, and the immunocompromised, potential progression to outcomes that in a normal medical environment would be prevented by basic clinical intervention. The food preservation science that addresses this problem is among the oldest and most extensively documented bodies of human knowledge in existence, predating written history, and representing the accumulated empirical wisdom of every human civilization that has ever needed to preserve food across time without continuous refrigeration. But the translation of this ancient and extraordinarily rich body of knowledge into the modern preparedness context has been systematically incomplete because the popularization of food preservation in preparedness culture has focused on a narrow subset of available methods, primarily canning and freeze-drying, while largely ignoring the broader landscape of preservation techniques that are in many cases more accessible, more applicable to a wider range of food types, more resilient to the infrastructure dependencies that compromise the most commonly recommended methods, and more deeply understood in their scientific mechanisms by the practitioners who use them most effectively. The forbidden in the title of this examination is not a reference to legal prohibition or deliberate suppression. It is a reference to the way that certain preservation methods have been effectively excluded from mainstream preparedness discourse by the combination of cultural unfamiliarity, regulatory conservatism, and the commercial interests of the preserved food industry, whose business model depends on selling pre-preserved food, rather than enabling households to preserve their own food through methods that are inexpensive, effective, and deeply scientifically validated. The science of food preservation begins with understanding what food preservation is actually preventing, because that understanding determines which methods are appropriate for which food types and which threat scenarios. Food deterioration, the umbrella category that food preservation opposes, has 4 primary mechanisms that operate simultaneously and that preservation methods address selectively depending on their mode of action. The first mechanism is microbial activity, the multiplication of bacteria, yeasts, and molds that decompose food components and, in the case of pathogenic organisms, produce toxins or cause infection.
The second mechanism is enzymatic activity, the action of enzymes naturally present in food that continue to catalyze chemical reactions after harvest or slaughter, producing quality degradation through processes like browning, softening, and flavor change that are distinct from microbial deterioration, but that can create conditions that accelerate microbial growth. The third mechanism is oxidation, the chemical reaction between food components and atmospheric oxygen that produces rancidity in fats, color changes in pigments, and the destruction of oxygen-sensitive vitamins and flavor compounds. The fourth mechanism is moisture migration, the movement of water within food or between food and its environment that produces textural changes, creates conditions favorable to microbial growth, and in some cases directly accelerates chemical deterioration reactions that require water as a reactant or medium. Every food preservation method works by controlling one or more of these four mechanisms, and the preservation methods that are most broadly effective are those that address multiple mechanisms simultaneously. Refrigeration works primarily by slowing microbial activity and enzymatic activity through temperature reduction, with secondary benefits for oxidation and moisture migration in sealed containers. Freezing extends this effect by essentially stopping microbial activity entirely and dramatically slowing enzymatic and chemical reactions, though enzymatic activity continues at low rates in most frozen foods, unless specific inactivation steps are taken before freezing. Canning works by combining heat sterilization, which destroys microbial populations, including heat-resistant bacterial spores in the case of pressure canning, with vacuum sealing, which removes oxygen and creates a physical barrier against recontamination. Each of these methods is effective within its specific operational parameters, and each has specific failure modes that the preparedness context exposes. Refrigeration and freezing fail immediately and completely when power is unavailable. Canning requires specific equipment, specific processing times and temperatures, and specific jar and lid materials that are themselves subject to the supply chain vulnerabilities discussed in other contexts. And all three methods depend on the preservation being performed before the food safety window has closed, which in a sudden grid-down scenario may not be possible for all of the perishable food in the household simultaneously. The preservation methods that fill the gaps left by these mainstream approaches are the ones that this examination addresses in the depth they deserve, beginning with the method that is simultaneously the oldest, the most scientifically understood, the most broadly applicable across food types, and the most consistently underrepresented in American preparedness culture: fermentation. The controlled microbial transformation of food through the activity of beneficial microorganisms, primarily lactic acid bacteria and certain yeasts, that produce chemical environments hostile to pathogenic and spoilage organisms, while simultaneously transforming the sensory and nutritional characteristics of the food in ways that have been valued by every human civilization that has practiced the technique. Fermentation is not a compromise preservation method or a primitive approximation of modern techniques. It is a preservation system of extraordinary sophistication that has been refined over millennia of empirical practice, and that modern food microbiology has validated and explained at the molecular level, with a completeness that leaves no ambiguity about why it works, how reliably it works,
and under what conditions it works best. The microbiology of lacto-fermentation, the specific fermentation process most applicable to vegetable preservation in a preparedness context, begins with the ubiquitous presence of lactic acid bacteria on the surfaces of fresh vegetables and in the soil and air of any normal environment. These organisms, primarily species of the Lactobacillus, Leuconostoc, and Pediococcus genera, are non-pathogenic, environmentally robust, and metabolically specialized for growth in the anaerobic, salt-tolerant conditions that the fermentation process creates. When fresh vegetables are submerged in a brine solution of appropriate salt concentration, typically 2 to 3% sodium chloride by weight of the water used, and maintained in an anaerobic environment, the lactic acid bacteria naturally present on the vegetable surfaces begin to multiply using the carbohydrates in the vegetable tissue as their energy source. Their primary metabolic product is lactic acid, which accumulates in the brine solution and progressively lowers its pH. As the pH drops, the environment becomes increasingly hostile to most other microorganisms, including the pathogenic bacteria that represent the primary food safety threat and the spoilage bacteria that produce the off flavors and odors associated with decomposition. The lactic acid bacteria are specifically adapted to survive and continue functioning in this acidifying environment, giving them a competitive advantage that allows them to dominate the microbial community in the ferment and to create the preservation conditions through their own metabolic activity. The elegance of this system from a preparedness standpoint is that it is entirely self-regulating and requires no external energy input after the initial setup. The lactic acid bacteria do the preservation work using the energy stored in the vegetable tissue itself, and the chemical environment they create is self-reinforcing, meaning that once the fermentation process has established sufficient acidity, the preservation conditions are maintained by the ongoing metabolic activity of the organisms that created them. A properly initiated lactoferment of vegetables will maintain food safety indefinitely at cool to moderate ambient temperatures, with the rate of fermentation and the final flavor profile determined by the temperature and salt concentration of the brine. At refrigerator temperatures, fermentation proceeds very slowly, and the preserved vegetables remain mild in flavor for months. At room temperature, fermentation proceeds more rapidly, and the preserved product develops more pronounced acidity within days to weeks. In a grid-down scenario where refrigeration is unavailable, room temperature fermentation is not a compromise. It is the design condition of the method, and the product that results from room temperature lacto-fermentation of vegetables is a food-safe, nutritionally valuable, calorie-contributing element of the household food supply that will remain safe and edible for weeks to months, depending on the specific vegetable, the salt concentration, and the ambient temperature. The scientific evidence for the food safety reliability of lacto-fermentation is not limited to traditional practice and historical record, though that record itself spans thousands of years across every inhabited continent and represents one of the largest bodies of empirical validation in human food history. Modern food microbiology has conducted extensive controlled studies on the pathogen survival characteristics of lacto-fermented vegetables under a range of conditions, and the results consistently confirm that properly executed lacto-fermentation produces pH levels and antimicrobial compound concentrations that are lethal to the primary foodborne pathogens of concern. Studies specifically examining the survival of Listeria monocytogenes, Salmonella species, and pathogenic Escherichia coli in lacto-fermented vegetable systems have consistently found that these organisms are eliminated or reduced to undetectable levels within the first days of fermentation as the pH drops below their survival thresholds. The pH of a properly fermented vegetable product typically reaches 3.5 to 4.0 within 2 to 7 days at room temperature, a level below the threshold of virtually all pathogenic bacteria of significance in food safety, and well below the threshold of 4.6 that the USDA uses as the boundary between high-acid and low-acid foods in its regulatory framework for canning safety. This pH achievement is critical to understanding why lacto fermentation provides a level of food safety assurance that is comparable to, or in some respects superior to, other preservation methods. The thermal processing used in water bath canning relies on the same pH threshold to ensure safety, because water bath canning at 212 degrees Fahrenheit does not destroy bacterial spores, only vegetative cells, and the safety of water bath canned products depends on the acidity of the product to prevent spore germination and toxin production after processing. The lacto fermentation process achieves the same pH endpoint through biological acid production rather than added acid, and it does so while simultaneously producing a range of additional antimicrobial compounds, including bacteriocins, hydrogen peroxide, and diacetyl, that provide additional inhibitory activity against potential spoilage and pathogenic organisms beyond the primary pH effect.
The result is a preservation system with multiple overlapping mechanisms of antimicrobial action, which in food safety engineering terms is called a hurdle system. And hurdle systems with multiple simultaneous antimicrobial mechanisms are among the most robust and reliable preservation approaches available, because the failure of any single mechanism does not compromise the overall system, as long as the remaining mechanisms maintain their effectiveness.
The practical application of lactofermentation in a preparedness context requires understanding the specific parameters that determine success and the specific failure modes that improperly executed fermentation can produce, because the same microbial processes that make lactofermentation an extraordinarily effective preservation tool can, if improperly managed, produce outcomes ranging from product quality failures to genuine food safety concerns. The primary control variables in lactofermentation are salt concentration, anaerobic conditions, and temperature, and each of these variables has a specific functional range within which the process reliably produces safe, high-quality preserved food, and outside of which the process can produce outcomes that are less reliable or genuinely unsafe. Salt concentration is the first and most critical control variable because it determines the initial microbial ecology of the ferment, creating selective conditions that favor lactic acid bacteria while suppressing the growth of other microorganisms that would otherwise compete with or outcompete the beneficial fermentation organisms. Salt concentrations that are too low, below approximately 1.5% of the water weight in the brine, fail to create adequate selective pressure for lactic acid bacteria and allow a wider range of microorganisms to compete in the early stages of fermentation, potentially producing off flavors, reduced food safety assurance during the pre-acidification period, and in some cases, the growth of undesirable organisms that produce metabolic byproducts incompatible with a safe, high-quality end product. Salt concentrations that are too high, above approximately 5% of the water weight, suppress the growth of lactic acid bacteria, along with the undesirable organisms, slowing or preventing the fermentation process, and producing a product that is preserved primarily by salt rather than by biological acidification, which is a different and less reliable preservation mechanism for most vegetable applications. The optimal salt concentration range for most vegetable lactofermentations is 2 to 3% of the water weight, a range that is easy to achieve through direct measurement and that produces reliable fermentation initiation within 24 to 48 hours at room temperature.